Okay, now we'll look at binomial expansion and relate it to combination theory that we've just learnt. Now, binomial expansion is the expansion of two terms. So we'll look at a plus b to the power of n, and n can range from 1 onwards. So first of all, we'll do it when n is 1. So if we have a plus b to the 1, that is a plus b. And the coefficients, notice, is 1 and 1. When we have a plus b to the 2, this one here, if you expand that out, you'll get a squared plus 2ab plus b squared. And the coefficients are 1, 2, and 1. When you do a plus b cubed, you have to do it the long way. You can say a plus b cubed is a plus b times by a plus b squared. We've already worked out a plus b squared from this one here. So you can write a plus b squared out in full there, and we have to multiply that by a plus b. Now when you multiply by a plus b, the a gets multiplied into everything inside that bracket. So that will give a cubed 2a squared b, ab squared. And then you have to multiply the b into everything inside that bracket. So b goes multiplied there, there, and there, and then we'll give the last three, a squared b, 2ab squared, and b cubed. And then when you collect all your like terms, you can have a 2a squared b and an a squared b, that'll give 3a squared b, and an ab squared and a 2ab squared will give 3ab squared. So looking at the final answer, you can see the coefficients is 1, 3, 3, 1. They are the three coefficients, four coefficients. In general, we can actually have a pattern for these coefficients. If we look over to the next page, you can see that here are the coefficients we just worked out. There's 1 and 1, then there was 1, 2, 1, and then the next was 1, 3, 3, 1. And you can see a pattern that if you just add the two previous numbers on a diagonal, you get the next number. So 1, 1 plus 2, you get 3. Or 2 plus 1, you get 3. And you can see down here it can keep extending. So 1 plus 3, that'll give 4. 1 plus 4, that'll give 5. So it's the next value down on the next line is from the previous line, from adding the numbers on the diagonal. Now that's called Pascal's triangle, and they're all the coefficients when you expand a binomial expansion. Now the other coefficients, we have to look at the actual terms in detail. Let's look at a plus b to the 4. So a plus b to the 4, you can see you write the coefficient down, it's 1, 4, 6, 4, 1, because that's come from this row. Because when we're raising to the fourth power, we use the fourth row. Now the actual terms, you can see go down in a pattern. So if you look at the first one, we have a to the 4, and then it's a to the 3, a to the 2, a to the 1, and really nothing, which is a to the 0. So you start off with the highest power of a and you go down. Likewise with the b's, you actually start off with no b or b to the 0, and then you go b to the 1, b to the 2, b to the 3, b to the 4. So the a's go down and the b's go up. So you can use that to expand any binomial bracket. Okay, now also be aware that those numbers can be expressed as combinations. So on this page down here, they have the Pascal's triangle on the left, 1, 1, 1, 2, 1, etc. But that really is, in combinations, it's C01. Now they don't put the C's in, but that really stands for C11. If you do that on the calculator, you actually get the answer 1. Let's take another one, like say that one there, 3. That corresponds to this. This is C23. If you do that on the calculator, you get the number 3. And you can see the combinations. You can see that it is going for the first row, you have 1 up the top. Second row, you have 2 up the top. Third row, 3 up the top. And you just ascend from the left to the right. So the R value on the bottom of the C goes 0, 1. This goes 0, 1, 2, 0, 1, 2, 3, etc. So even if you can't remember the numbers, you can always use the combinations. Now that comes in handy with a formula, which is on the next page. And here's the formula for a plus b to the n. To see that formula, let's look at it for all the cases to spot a pattern. So firstly, if we had n is 1, it would be a plus b to the 1 equals, it's a to the 1 plus, and we've got C01, which is 1, plus, and then we bring start bringing the a down, which is a to the 0. And here we've got b to the 0, and we bring that up, so that's b to the 1, and the c, it's going to be C11. So that's the order, which actually is, if you just C01 is 1, and so that will reduces to a plus b. So that's a basic one. The next one is a plus b all squared. Using the same formula, we'll have C02, these are the coefficients, and then it will be C12 and then C22. Now the a's and b's, you start off with the highest power for the a's, so it's a squared, a1, a0, and the b's, you start off with the lowest, b0, b1, b2. Now if you simplify all that, C02 is 1, so that's a squared plus, this one here is, missing out a plus there, this one here is 2, C12 is 2, so that's 2ab, and finishing off with b squared, and that we saw that before. Now we go to 3, a plus b all to the 3. So the coefficients are C03, C13, C23, C33. And the a's, you start off as a cubed, and you start reducing a squared, a1, a0. With the b's, you start off with 0, then you go to 1, then you go to 2, then you go to 3. Now working all of that out, that will be 1, so it actually ends up being a cubed plus 3a squared b plus 3 a b squared, and then plus b cubed. And in general, if we keep doing that process, you can generally just say that a plus b to the n is equal to, now you're going to start off with c0n, a to the n, and b to the 0, plus, then will be c1n, and then will be a to the n take 1, and then the b starts going up to 1, and then c2n, and then will be a to the n take 2, b to the 2, and then we can go plus dot 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 dot. We can go to a general term, we'll call it CR. Now CR to the n is going to be a to the n take r, all to the b to the r, plus, and we can go dot 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 all the way to the end, which is going to be CNN, and a to the 0 and b to the n. Now that's our general formula. You can see it in the textbook. They have written it there. I've done it in full form to see the pattern. You can see they've left out C0n in their a to the n at the front there, but you can see the pattern a lot easier if you use this method. Alright, so using that formula you can now answer any question that is a binomial expansion. So for example, these ones here, you can look at the worked examples. So there's the worked example 11, worked example 12. You can try 8F, pause the video, try 8F, and then come back and have a look at the solutions. And here are the answers to 8F, question 1 and question 2.